Good morning, everyone, and welcome to this Hydrock webinar presentation, which is amongst a series of webinars hosted by our various disciplines. This is the second webinar hosted by our Fire Safety Division, the first of which was titled The New Fire Safety Bill and What It Means for Your Building. For details of our previous webinars and our upcoming webinars, I will direct you to our website, www.hydrock.com, where you can find video recordings of our previous fire safety webinar as well. Firstly, I'd like to introduce myself. My name is Chris Allery. I'm a technical director with the Fire Safety Division at Hydrock, primarily focused in the South of England regions, and I'm based in the London office. So without further ado, I'll start the presentation. This presentation, delivered on behalf of our Fire Safety Division, is titled Fire Safety, the Future Use of Timber in Construction. The presentation aims to discuss the multitude of benefits of mass timber construction, the fire safety industry's concerns for mass timber as a construction material, including an update on recent government guidance and regulations, and what the future might look like for the use of mass timber in construction. The structure of the webinar will be as shown: a brief introduction, an overview of Hydrock and the Hydrock Fire Safety Division, a look at a timeline of significant events up to and after the Grenfell Tower tragedy, as it's good to understand how we got here, a closer look at the aspects of this timeline that had an effect on mass timber construction, a review of the various types and benefits of mass timber construction, a look at the key concerns of mass timber construction within the fire safety industry, what the current situation is and where we are right now, and a discussion regarding what the future might look like. Before we start, I want to outline some key limitations to this presentation. You will have the opportunity to ask questions via the message function or respond to a few questions at the end of the presentation. However, we will respond to all questions within 7 working days. Could I please ask that when asking questions, you include your name and details so we know who to respond to. We will not be responding to any questions relating to the ongoing public inquiry, Grenfell, and the territory of this discussion will be England and Wales only, since the MHCLG has no governance in Scotland or Northern Ireland. So, moving to the introduction. The objectives of this webinar are to review the opportunities for timber construction and the benefits it provides, the obstacles for its use within the construction industry at this time with regard to fire safety, what the future looks like from today, and what we feel needs to happen. In this section, I will provide a brief introduction to Hydrock and the Fire Safety Division. Hydrock is a multidisciplinary engineering design consultancy with over 500 staff operating from 16 UK offices, including Manchester, London, Birmingham, Bristol, Cardiff, Glasgow and Leeds. We provide a number of engineering services across the built and natural environment. Hydrock's Fire Safety Division was founded in 2017 and now has 25 fire safety professionals working in many of the UK's regional capitals, including London, Bristol, Cardiff, Manchester, Birmingham and Glasgow. Our team has a broad range of expertise and experience ranging from fire engineering, fire risk management, nuclear industrial fire safety, expert witness, structural fire engineering, and specialist services, which includes the computational fluid dynamics modelling, blast design, and evacuation modelling. We have a few examples of projects the Fire Safety Division at Hydrock have worked on and the types of services we provided. Phase 1, Hunslet Road in South Bank, Leeds. This was a residential development initially consisting of 315 homes with room for expansion, commercial, cafe, gym and retail spaces. We provided fire engineering, fire risk management and specialist services, notably computational fluid dynamics modelling, the extended residential common corridors and mechanical smoke ventilation systems. Hangars 85 and 86 for Dyson in Wiltshire. This was a fast-paced conversion of former derelict military aircraft hangars into a modern contemporary workspace and research and development facilities for their electric car project. We provided fire engineering and specialist services, notably structural fire engineering analysis. The new engineering building at the University of the West of England in Bristol, the scheme included engine test cells, wind tunnels, dedicated learning spaces to accommodate a wide range of engineering disciplines, including composite manufacturing, machining and metrology. We provided fire engineering services and specialist services, including Monte Carlo analysis and CFD modelling again. IAPS, or the Institute of Advanced Automotive Propulsion Systems building at the University of Bath. It was a new global centre of excellence to deliver transformational research and development for automotive propulsion technologies, which will support the development of the next generation of low-carbon vehicles. We provided fire engineering and fire management services throughout design and construction. So, as I mentioned in the introduction, before discussing mass timber construction specifically, I would like to take you through a timeline of significant events and advice before and after the Grenfell tragedy, which has led to where we are in the fire safety industry today. For those of you who attended our first webinar, you may recognise the next slide. The timeline you can see now is mainly focused over the past 3 years since Grenfell. The timeline includes all of the key advice issued by the government, as shown in green, and the significant fires that were considered to include fire spread via the external wall system as displayed by a flame. The slide is busy, but that is purposeful, as that is what building owners, building designers and fire safety professionals have had to navigate over the last 3 years, which has been challenging for some. However, I would like to highlight the Lacanau fire back in 2009 at the start of the timeline, reason being that there was no government advice or response or change of legislation after this fire, even though the fire resulted in a number of deaths due to fire spread across the external walls. For the rest of the timeline, the significant advice outlined within the timeline was issued by the government swiftly after Grenfell. All of the guidance notes issued by the Ministry of Housing, Communities and Local Government have been consolidated into a single document, which was issued on the 20th of January this year. We'll look at that document in closer detail later in the presentation. There are a number of omissions from the timeline that I would like to highlight, as these include significant advice and details. The Grenfell Inquiry Phase 1 report, the government response to the Grenfell Inquiry Phase 1 report, the independent review of building regulations and fire safety, also known as Judith Hackett interim and final reports, and the government response to the Judith Hackett reports. The Grenfell Tower didn't contain any timber elements within the external wall construction. However, the tragedy obviously did spark a review and discussion into the use of combustible materials in residential external wall construction, and quite rightly set the fire safety industry on this journey. The Building Amendment Regulations 2018, which came into force on 21st of December 2018, banned the use of combustible materials, which is defined as anything Class A2 or worse, in external walls of high-rise residential buildings with a story more than 18 metres above ground level. The document defines the external wall as the full build-up from the external layer to the internal room lining, excluding any decoration or other finish applied to the internal lining surface. The document does include a number of items within external walls of qualifying buildings which are exempt from this ban. However, these do not include any form of timber used for building structure or cladding. Therefore, essentially, the amendment to the building regulations has banned the provision of any timber within external walls in high-rise residential buildings, whether used for structural or cladding material. Advice Note 22 was released by the MHCLG on the 18th of July 2019. This advice note was released for building owners of high-rise residential buildings that contained high-pressure laminate cladding panels. At the time, MHCLG had conducted full-scale BS 8414 tests with HPL cladding panels and found that the wall systems could achieve performance criteria BR135, providing the HPL achieved Euro Class B with regard to surface spread of flame and was combined with a non-combustible mineral wool type insulation. The document advised that high-pressure laminate cladding systems that achieve Euro Class C or worse, or where they were combined with combustible insulation products, would be unlikely to achieve the performance criteria BR135 in a full-scale BS 8414 test, and would therefore unlikely achieve an acceptable level of safety. The MHCLG then released their consolidated advice note on the 20th of January 2020, as I mentioned earlier. This document brought together and updated all advice from the previously issued advice notes, into a single document for building owners of multi-storey, multi-occupied residential buildings. One of the key differences between the advice within the consolidated advice note and previous advice notes regarding external wall construction is that the new consolidated advice note considered buildings of any height rather than just buildings with a storey more than 18 metres above ground level. The document explains that requirements, previous and current, for buildings with a storey more than 18 metres above ground level are clear, and owners should confirm their products installed in their buildings genuinely complied with these requirements. For example, had a valid BS 8414 test demonstrating performance criteria of BR 135 or product test certification for limited combustibility or better. However, the document also states that the external wall construction of buildings with no storey more than 18 metres above ground level should be risk assessed to confirm the functional requirement B4 of the building regulations is met. Functional requirement B4 being the external walls of the building shall adequately resist the spread of fire over the walls and from one building to another, having regard to the height, use and position of the building. The new advice note therefore advises designers and fire safety professionals to consider the risk presented by combustible materials in external wall construction to confirm the functional requirement of the building regulations is met in buildings of any height, even where less than 18 metres. Before we go into too much detail regarding properties and performance of timber, I just wanted to go through some of the main types used in construction. The more common types I'd like to cover in the presentation are dimensional solid timber frame, glue laminated timber, cross laminated timber, laminated veneer lumber, dowel laminated timber, and nail laminated timber. Timber frame construction involves the use of solid timber to form a structural frame with a similar approach to that of a steel frame, including beams, columns, and rafters, etc. Glue laminated timber, or also known as glue lam, is comprised of a number of layers of dimensioned timber that are bonded together with structural adhesive to increase the structural performance. Generally, the grain runs parallel to the main axis of the member. By laminating a large number of smaller timber elements, a single, larger, strong structural member is manufactured. This type of timber construction is often used for beams and columns where appropriate. Cross-laminated timber, also known as CLT, is manufactured from lower grade timber offcuts, which are reduced to strips that are finger jointed and glued in perpendicular layers under high pressure. In the factory, the solid CLT panels can be cut to the required shape and size. Laminated veneer lumber, also known as LVL, is manufactured from thin, peeled veneers of wood, usually 3 mm thick, and glued with structural adhesive. Panels of LVL are cut into structural members, which have a high strength and stiffness. This type of timber construction is often used for beams and columns where appropriate, similar to that of glue lam. Dowel laminated timber, also known as dowel lam or Brechstaffel, is fabricated from softwood timber layers stacked in one plane and connected with hardwood timber dowels. This relatively simple manufacturing method has the potential to utilise lower grade timber that would otherwise be unsuitable for use in construction to form load-bearing, solid timber wall, floor and roof panels. And nail laminated timber, or NLT, similar to dowel lam, however, nails are used to connect the timber planks into a solid wood panel. We know timber has a host of benefits when used in construction, some of which I'm going to cover in this section. From a sustainability perspective, the rotation of construction timber harvesting varies depending on the location, type of wood and intended use. However, it typically ranges from around 35 to 70 years. That kind of time frame may be considered significant in a human lifetime scale, however, is a mere blink of an eye in any geological timescale with regard to replenishment of rocks and ores for other building materials. That's the basis, the reason timber is considered the only widely used building material that can be considered truly sustainable. Environmentally, during the growth phase of a tree, carbon dioxide is sequestered into the tree via carbon dioxide processing in the canopy and uptake through the soil. Utilising the harvested timber for long life cycle products, such as building construction, allows the benefits of this sequestered carbon dioxide to be maximised. The rate of uptake of carbon dioxide into trees is highest during the growth phase, and therefore logic dictates that the greatest environmental benefits from forests with regard to removal of carbon dioxide from the atmosphere can be achieved by using managed forests where trees are kept growing. They are then harvested for long life cycle products, and new trees are planted to maintain constant growth within the forest. Mass timber buildings are also roughly 25% faster to construct than concrete buildings and require 90% less concrete construction traffic. Since mass timber panels are prefabricated and then assembled on site, buildings made from mass timber have much shorter project timelines. And life cycle assessment studies consistently show that wood outperforms steel and concrete in terms of embodied energy, air pollution, and water pollution. From a construction perspective, as I mentioned previously, mass timber buildings are approximately 25% faster to construct than concrete buildings. It's also considered a highly versatile material in both its structural performance and appearance. With new engineering techniques, as I discussed previously, timber can be manufactured to achieve almost any structural objective, from beams and columns to walls and floors with long unsupported spans due to its high strength and weight ratio. We'd all agree that timber is aesthetically appealing in design and offers huge versatility in appearance, and we have significant evidence that timber is a durable construction material with a catalogue of buildings lasting centuries, even without modern protection techniques. Timber construction allows manufacturing and prefabrication off-site, reducing the installation time and overall construction program and allowing buildings to be occupied sooner. Timber also generally requires less demand for skilled worker resource. Current cost estimates of high-rise timber buildings to date have been slightly warped by additional costs associated with the research and development due to the current innovation of the design. However, with greater understanding and supply availability, timber construction seems to be a highly cost-effective construction approach, even for tall buildings. Fire is, of course, the first concern that comes to mind with wood construction. However, there's a great deal of evidence to suggest mass timber is actually safer in a fire than steel with regard to structural stability in a fire scenario. At high temperatures, timber decomposes, which results in char and the release of flammable gases which ignite and result in fire. However, the char formed on the surface of the timber helps to protect and insulate the unburnt wood below and maintain the element's structural integrity and low burn capacity. Wood burns slowly at approximately 0.65 millimeters per minute, and it's even possible for the char layer to reach a thickness sufficient to halt the production of flammable gases and self-extinguish the fire. There are two key strategies to providing adequate fire protection to timber performing a structural or compartmentation role. The first is full encapsulation. This involves encasing the timber within sufficient non-combustible products, such as plasterboard, to prevent pyrolysis of the timber for the entire duration of the required fire resistance period. In this case, the combustibility of the timber need not be considered. The second is to demonstrate auto-extinction will occur. This involves demonstrating that the timber char will self-extinguish in a compartment fire scenario prior to the integrity of the timber element failing. This may involve the provision of partial encapsulation to prevent pyrolysis of the timber for an initial duration. In comparison, steel, for example, on the other hand, begins to melt when it reaches a critical temperature at around 1300 degrees C and loses a significant extent of its load bearing capacity at temperatures above 550 degrees C. Concrete structures generally perform very well in fires. However, concrete is a complex material and its properties can dramatically change when exposed to high temperatures. For example, compressive strength of concrete is quickly lost beyond extreme temperatures above 600 degrees C. Concrete can also suffer from a unique effect called spalling, which results from moisture in the concrete fracturing the concrete as it escapes in the form of vapour at high temperatures. This can occur at temperatures as low as 200 degrees C and is of particular concern in high strength concrete. Cross-laminated timber, or CLT, has become widely popular in the modern construction industry due to its improved sustainability statistics compared to traditional building methods and ease of installation, as I mentioned previously. CLT has a wide range of applications and can be used as part of a hybrid structure or as a sole building material. CLT is primarily used for walls, roofs and floors. Because of its variance in thickness, it's highly versatile and does not sacrifice integrity in place of sustainability. Its reduced weight when compared to traditional materials like concrete gives it considerable advantages in terms of total building weight and allows additional stories on a foundation of the same size. The use of CLT is well documented in almost every sector, and there are numerous examples of CLT in everything from high-rise buildings and large commercial office space to single-storey dwellings. A great example of CLT in construction is the East London Tower, Stadthouse. It's a 9-storey residential building in Hackney, London. The floors, ceilings, elevator shafts and stairwells are made entirely of CLT. And when built in 2009, Stadthouse was by far the world's tallest modern timber building. Another example is Brock Commons, Phase 1, which is a tall timber hybrid student residential building at the University of British Columbia, consisting of 18 stories. The building consists of 17 stories of mass timber construction above a concrete ground level and has 2 concrete stair courts. The timber floors are 5-ply CLT panels supported on glulam columns. That approach removed the need for load-bearing beams. Steel connectors were used to connect columns between floors to avoid vertical load transfer through the CLT slabs. The CLT and glulam components were completely encapsulated within 3 to 4 layers of gypsum board. It's estimated that the timber construction over traditional building methods saved more than 2,400 tons of carbon dioxide from going into the atmosphere. It's also estimated that the cost differential for this project as a result of utilising timber hybrid structure was approximately 8%. However, as I mentioned before, a large proportion of this was due to the significant research and development costs as a result of the innovative approach at the time of design. Construction design incorporating a combination of timber, concrete and steel provides a variety of benefits, including improved strength to weight ratio for the building, which is particularly advantageous where ground conditions are limiting aspects such as building size and height, and the ability to utilise long unsupported spans into the design, which benefits from an architectural and building services perspective. There are many aspects of the use of timber in construction that are of concern and require consideration during design, such as maintaining a moisture content less than 20% during site works, the poor performance of timber with regard to acoustics and thermal efficiency compared to other materials such as concrete, and subsequent enhanced measures required to meet these requirements. However, for the purpose of this presentation, I'll focus on the fire safety aspects only. There are a number of aspects of timber construction that require detailed consideration in design to ensure an acceptable level of safety is achieved. Some are delamination, decay phase continued thermal penetration, and more recently, fire spread via external walls. As mentioned previously, timber achieves a structural fire protection by use of its charring rate. The exposed areas of timber char at high temperatures, protecting the unburnt timber underneath to maintain its structural integrity in fire. However, laminated forms of timber construction, where the layers are held together with structural adhesive, such as glulam, CLT and LVL, they're liable for delamination in fire. Research and testing has been conducted on the influence of the temperature-dependent material properties of the adhesive on the resistance of CLT beams exposed to fire. It's been demonstrated that the fire behaviour of CLT panels is strongly influenced by the behaviour of the adhesive that is used for the CLT panels bonding system. CLT panels manufactured with a less temperature-sensitive adhesive show that charring layers almost remained in place throughout fire tests. Tests with varying extents of exposed CLT in room fire have demonstrated that the exposed timber increased the heat release rate, fire duration, and potential exterior flame propagation where ventilation conditions were low. However, the tests have shown that limited areas of exposed timber might be acceptable subject to CLT type and location of exposed surfaces. Further testing and greater understanding will inform the safe extent and configuration of exposed mass timber surfaces within compartments. Structural timber must achieve the required performance for occupant and firefighter life safety. These considerations have led to a renewed impetus in timber fire safety engineering research. They require moving beyond the fire testing of individual elements and addressing questions about whole structure behaviour. However, not many large-scale tests have been carried out to date. In compartment fires with boundaries consisting of exposed mass timber surfaces, such as CLT walls and floors, test evidence suggests that the thermal penetration depth may continue to increase after the compartment fire has been extinguished. This continued thermal penetration results in reduced load-bearing capacity and increased potential for structural collapse during the decay phase of the fire. Facade systems involving timber as a material are combustible and should be detailed and designed for fire safety to remove the risk of fire spread over multiple stories. To ensure a fire-safe design, it is considered best practice to design in consideration of evidence from research and testing. But like I said, it's evident that a significant extent of research and testing has been undertaken for the use of timber structure and compartment fires with regard to structural integrity. However, we still need to do more research. However, limited research has been conducted to date to review the impact of timber and external wall construction and its potential contribution to flame spread across the external wall to multiple areas of the building and potential separate fire compartments. So the situation right now, as I mentioned before, there's a real appetite in the industry right now to utilise timber as a construction material for all the benefits it provides, such as ease of installation and aesthetics. But most importantly, the environmental advantages. The UK is a target to achieve net zero emissions by 2050, with a number of areas moving towards an even more ambitious target of 2030. Timber has a key role to play on both sides of the net zero balance due to the use of sustainable forestry, removing CO2 from the atmosphere, and less carbon intensive manufacturing, distribution and construction processes, resulting in reduced CO2 production. Data suggests that the embodied energy of primary production of dimensional softwoods from Sitka spruce is approximately half that of structural grade steel. However, the 2018 amendment to the building regulations has already banned the use of timber within the external walls of relevant residential buildings with a story more than 18 metres above ground level. There's currently no distinction in this ban between the timber used as structural material and timber used as a cladding element. The MHCLG ran a consultation earlier this year to review the ban, from which they are currently analysing the feedback. We've not had a formal response. This consultation questions whether hotels, hostels and boarding houses or any other building type should be included within the ban, whether the height threshold of the ban should be brought down to buildings with a top story more than 11 metres above ground level or any other height, and if any additional components should be included within the list of exemptions from the ban. The latest revisions of approved document B and latest advice from the MHCLG within their consolidated advice note state that in relation to buildings of any height or use, consideration should be given to the choice of materials, including their extent and arrangement used for the external wall or attachments to the wall to reduce the risk of fire spread over the wall. This is obviously relevant and of concern in buildings containing a sleeping risk, however should be considered in buildings for all purpose groups and height, particularly where the buildings contain compartment floors designed to prevent fire spread between levels. This includes tall buildings or where some occupants not within the compartment of fire origin are designed to remain in place for a period of time, such as commercial buildings with a phased evacuation strategy. As I mentioned before, it's evident that a significant extent of research and testing has been undertaken for the use of timber with regard to fire safety, such as its structural performance in fire, its ability to act as a fire-rated wall or floor, and how to provide passive fire protection. However, limited research has been conducted to review the impact of timber in external wall construction and its potential contribution to flame spread across the external wall to multiple areas of the building and potential separate fire compartments. Based on that, what does the future look like? In the short term, timber has been banned conclusively within external walls of residential buildings with a story more than 18 metres above ground level, and this ban may be extended to include other purpose groups with sleeping risk, and the height threshold may be reduced to 11 metres. At Hydrock, we feel that this was the right decision by the MHCLG due to the lack of evidence demonstrating timber's suitability in external walls with regard to life safety. Even with the evidence of sustainability and environmental benefits, we cannot jump ahead and let the use of timber construction go unchecked or consider amending the conditions of the ban without scientific basis. Therefore, based on the benefits I've discussed within this presentation, I think it's imperative that as an industry, we find a solution to the use of timber in buildings. This will involve further research and testing into the effects of timber within external walls. The testing will need to include not just types of timber cladding, where multiple tests have already been carried out by the BRE and MHCLG, but more importantly, the use of structural timber, including encapsulated versus exposed timber, and the various types of engineered timber and structural framing strategies, such as CLT walls and floors, glulam and LVL columns, dimensional timber frames, and hybrid systems. A number of tests have already been commissioned, including a testing program by 3 of the largest CLT suppliers, KLH, Binderholz, and Stora Enso. The testing program aims to provide scientific evidence of product performance that will allow government to view CLT as a building material suitable for buildings, not just over 11 metres, but over 18 metres as well. The testing will take 18 months, and the data is due to be released as and when it becomes available. But all in all, it's down to us as an industry to push for the required research to unlock this vital piece of the net zero puzzle. Until then, there is still plenty of opportunity to utilise timber in construction in buildings with a simultaneous evacuation strategy and no sleeping risk, where the rate of flame spread across the external walls is of less concern. However, still needs to be considered. There is potential to utilise timber construction within any building or external wall that is not subject to the government ban, providing it's considered as part of a fire risk assessment by a fire safety professional. That is the end of the presentation. I just wanted to take this time to thank everyone who joined and hope you found it useful and informative. If you could send through your questions, I'll take a look and answer a few now, but we will respond to all questions within 7 working days. And please remember to include your name and contact details so we know who to respond to. So I'm just having a look at questions. So there's a question here from Bill Hay at Astute Fire. Thanks very much for joining, Bill. I really appreciate it, and thanks for the question. Do you support the ACAN opposing the government's proposal to ban the use of safe structural timber in the external wall of buildings with a floor above 11 metres if based on a science-based approach? It's a good question. I'm not familiar with the ACAN, but essentially I think we're all for the introduction of deviations and exemptions to be brought into the ban, but they need to be based on scientific evidence and numerical data. It can't just be based on a passionate decision based on the sustainability and environmental benefits of timber, not to say that that's anyone's view. I personally think eventually we'll have to remove the ban and make timber available for use in buildings of all height and all purpose groups, residential, tall buildings, but only when it's proven safe to do so, which at this stage it's not. The ban itself is a necessary and unfortunate but necessary control on the use of timber, whilst its performance and behaviour in external walls is unknown and not yet proven. I also think the government has quite a large responsibility to undertake a lot of this research and testing that's going to be necessary to unlock the use of timber in order for us to hit the net zero targets. So that answers the question. Just looking through some more. So the question here from Brian Tierney, Building Control in Glasgow. Thanks very much, Brian, and thanks again for joining the presentation. What are the implications of fire damage of a timber wall or floor? Is there any complications in re-entering a building using timber construction compared to steel or concrete construction post-fire due to the charred layer of continued thermal penetration? It's an interesting question. I suppose my answer would be that there shouldn't be any additional complication with timber and re-entering a building post-fire. The functional objective and performance criteria for structural fire protection for timber, even though it's combustible, are the same of that for steel or concrete. Essentially, that the building should remain stable for the entire fire duration, indefinitely, not just for the 30, 60, 90, 120 minute duration. That's not how long the building should last for. It should last for indefinitely. Structural fire protection is designed for burnout. So as long as those specific principles that are specific to timber, such as charring and continued thermal penetration in the decay phase, are considered throughout design, then the building should be designed to satisfy that functional objective of the structural fire protection to remain standing indefinitely. So there shouldn't be any additional complications, would be my answer. Is there any more questions? A question from Jeff Ellerman at Butler & Young. Thanks, Jeff. I really appreciate you joining the presentation. I hope you found it useful. Your question: should care homes under 11 metres consider the risk of timber within the external wall construction, even though it has not been banned for these buildings? I think it should always be considered for any building type, height or purpose group. But especially where the occupants within the building are vulnerable, I definitely agree. Even the latest MHCLG Consolidated Advice Note seems to group together the risks associated with buildings with vulnerable occupants or where a progressive horizontal evacuation strategy is used. It seems to group them together with the same sort of risk level as buildings more than 18 metres above ground level. So it's definitely something that needs to be considered in design. That's not to say that timber can't be used in low-rise residential care homes. It just needs to be considered in design to ensure that an adequate level of safety, taking a holistic view of the building, is achieved for the residents. So I've answered a few questions. If you want to keep sending through your questions, though, please remember to include your names and details so we know who to respond to, and we will respond to any further questions later within 7 working days. But I really hope everyone enjoyed the presentation. I found it informative. Thank you.